So in this video, we'll be looking at aromatic halogenation. That is, the reactions between benzene and different halogens. So that's going to include things like chlorination and bromination. And these aromatic halogenation reactions are going to be examples of EAS reactions. So EAS, that is electrophilic aromatic substitution. So these electrophilic aromatic substitution reactions include things that we've seen in former videos, right? In previous videos, we looked at benzene sulfonation as well as benzene nitration. These are all examples of electrophilic aromatic substitution. So you'll notice some similarities here that between the other reactions that we've already encountered. So these reactions are simply involving a benzene, which attacks some sort of electrophile, and then that electrophile group is going to be replacing the hydrogen that we normally see on a benzene. So in the case of bromination, which is what we'll start off with, we're going to be taking a benzene, which has its 3 double bonds, right? And we have our hydrogen here. And this benzene, we're going to be replacing the hydrogen on the benzene with a bromine, as the name would suggest, which is why it's called bromination, right? So we end up with a bromine. So how are we getting this bromine onto our benzene? Well, we're going to be reacting our benzene with Br₃, right? Br₃, as well as FeBr₃. So this combination of Br₃ and FeBr₃ reacting with our benzene is going to give us our product in bromination. So what exactly are we doing with our bromine and FeBr₃? Well, we're using them to produce a electrophile. And that electrophile is what is going to react with our benzene, ultimately producing our product. So let's look at what the generation of this electrophile looks like. Well, we're going to start off with our bromine. So this is Br₃. So that's 2 bromines, each of which has, their lone pairs, these 3 lone pairs. And this is going to react with our FeBr₃. FeBr₃. And all we're going to be doing now is just forming a bond, right? This bromine is really just latching onto this FeBr₃. So we're going to end up with an electrophile that looks something like this. Right? And we just have 2 lone pairs there. And 3 on this one. Right? So we have a plus here and a minus on our iron. And this here is going to be our electrophile. This is the electrophile, right? That we're going to be reacting with our benzene. So for bromination, now that we have our electrophile, all we have to do is react with the benzene in an electrophilic, which this is our electrophile, aromatic substitution. So the aromatic is referring to this aromatic molecule here, our benzene. And what we're doing in the substitution is, as we said before, we're substituting the hydrogen here for some other group, and in this case that's going to be a bromine. So if we're starting off with this, we now have to draw our electrophile, which we just generated. So that's going to be our bromine bonded to our FeBr₃. Just keep in mind our charges here. So what is going to happen, like we've seen in other EAS reactions, is we're going to have this benzene here attack the bromine, causing these electrons in this bond to collapse over here. So now what we're going to have is this intermediate, this unstable intermediate form. And why is it unstable? Well, because we've lost this double bond here, and with the loss of that double bond in the benzene, our benzene is no longer aromatic. So here we have these 2 double bonds. We have the hydrogen, we have our bromine that we have just formed a bond with through the attack to the electrophile, and we still have this other hydrogen here. However, this carbon also now has a positive charge. So now what we're going to have to do is we're going to have to react with a base. What base are we reacting with? Well, we can simply react here with our FeBr₄, right? FeBr₄, that we have this remnant of this electrophile, right? This should now have 3 lone pairs. So all we have to do is this here is going to attack our hydrogen, causing the causing the electrons in this bond to collapse, which is now going to give us our final product, which is going to look something like this, right? We have now retained or regained the aromaticity of our molecule. So this is our benzene with 3 double bonds, and in place of our hydrogen we now have our bromine, and this is going to be our product. So this is the mechanism for this bromination. Now chlorination is going to follow in a very similar manner. So for the chlorination of benzene, we're going to again start off with a benzene, its hydrogen, and by the end of this reaction we'll end up with a benzene that in place of the hydrogen will be a chlorine. As the name suggests, chlorination is going to be the addition of a chlorine. So how do we do this? Well, we're going to be using Cl2 as well as AlCl₃. Again, you could also use FeCl₃, but for this reaction, let's just use AlCl₃ just for some variety here. So we'll start off. The first step, right, is going to be forming that electrophile. We need the electrophile in order for this reaction to even occur. So we're going to form the electrophile in our first step here, or the first part of the mechanism that we're showing. So we'll start off with our Cl, right, or Cl2 rather, right, which we have 2 chlorines bonded to each other, each still having 3 lone pairs. And this is going to react with our AlCl₃. So again, like we saw in the previous reaction with bromination, here we're going to have our chlorine simply latch on. So we're forming a bond here. And this is going to end up giving us our electrophile. So we have 3 lone pairs here. This is bonded to an AlCl₃. This has 2 lone pairs, and thus a positive charge, and our aluminum here will have a negative charge. So this is going to be our electrophile, very similar to what we saw in the bromination reaction. So this is the electrophile. So now let's see how we react in this electrophile with our benzene. So we start off with our benzene molecule. Let's draw the 2 hydrogens here. We have 1 and 2, and now we'll draw out our electrophile. So we have Cl, AlCl₃. Let's just draw those lone pairs where appropriate. We have a plus charge and a minus. So what we'll see, as before, we have our benzene attack the chlorine, causing these electrons in the bond to collapse onto this chlorine here. We now end up with this unstable non-aromatic intermediate here, which will still have this hydrogen and this hydrogen, but we will also now have a chlorine here, and this carbon will have a plus charge. So now we have to react with some base. Just like before, we could react with our AlCl4-, but just generically, if we want to react with a base, this base would attack our hydrogen. The hydrogen, or the bonds between the electrons forming the bond between the hydrogen, the chlorine, and the carbon here are going to collapse, reforming our double bond. This is going to occur very fast. This is a quick step because we are reforming an aromatic molecule. This is a lot more stable. We're going from something that is unstable to something very stable. So this is going to happen a lot faster. It's less energetically demanding. It's exothermic, as opposed to the former steps, which are endothermic, or which is endothermic. So anyway, what we end up with is our product here, a benzene with 3 double bonds, right? It's a benzene. And in place of our hydrogen, we have our chlorine. So this is the chlorination reaction. So these are 2 examples of aromatic halogenation reactions. So hopefully these mechanisms aren't looking too difficult. Again, there you can see a lot of similarities between what we've seen from sulfonation to nitration, bromination, chlorination. These all should look very similar, because the generic step, all we're doing generically is we're taking some benzene with its hydrogen, reacting that with some electrophile, which again, this double bond is going to attack the electrophile, giving us an intermediate, this unstable intermediate, might I mention if I haven't said that enough already, with our hydrogen here and our electrophile. We then react with some base, which attacks the hydrogen. This should have a plus here, sorry. Collapsing the hydrogen, collapsing these electrons here, reforming that double bond, and giving us a product that looks something like this. So this is just the generic reaction that we see happening in these EAS reactions. So they are going to be very similar. Anyway, that brings us to the end of this video. Hopefully everything made sense. If it was useful, please show your support by liking and subscribing, and leave in the comments any questions you may have, as well as suggestions for future videos, and I will see you in the next one.